So welcome to the lecture. We will begin the module 3 of the first part of the course. So we have already discussed necessary ingredients from Newton's gravity as well as special relativity. So based on that, we now will try to construct a Lorentz covariant generalization of Newtonian's theory of gravity, or the Poisson equation for gravity, which is of this form. So we will start from this equation and impose some physical condition or restriction and try to get a tensor rank equation which will be explicitly Lorentz covariant and see what are the implication of that. So before doing that, as a warm-up exercise, let's start with the Poisson equation that appears in the context of electrostatics. And we will impose certain physical condition on it and try to see whether we get the Maxwell's equation or not. And in the process, we will learn some interesting lessons which will be useful when we do this same exercise for the Poisson equation for gravity. So let's begin with the case of electrostatic. So let's pretend that we only know the equation of electrostatic, which is nothing but minus Laplacian of the electric scalar potential is equal to the charge density. Now we want to make it Lorentz covariant. To do that, we will impose certain physical condition, which stems from the fact that there are some theoretical consistency that has to be maintained, as well as some things which come from the observation or from the experiments. Okay. So if we want to make this equation Lorentz covariant, first of all, let's look at the right hand side of this equation. So there's the charge density C. Now we know from our previous discussion that together with charge density and the charge current, we can write them in terms of a 4 vector, which we called J mu. Charge current density 4 vector, right? So remember that J mu is of this form. Now, if J mu like rho will be the source of the Maxwell field. So on the left hand side, it will be some function of the Maxwell field. So now we expect that the field will have the same Lorentz structure that of the source. So we denote the field by A, which have only one Lorentz index, just like the source. In fact, this A and J form a canonical conjugate pair. They have the same number of Lorentz index, and you can form a scalar out of it by contracting the Lorentz index and write an interaction term in the background. Now, in general, this left hand side will be some function of A and its derivative, and so on. Sorry. Something like that. A and all possible derivative terms. So now we have to try to fix this function. How do you do that? First of all, note that this Poisson equation is linear in phi. So we expect this function f should be linear in a mu. And also remember our previous discussion. So most of the equations are at best of contain second two derivatives. So this f should be linear in A, and we'll have term not more than two derivatives of A. By two derivative, we means two derivative of space and two derivative of time, because special relativity taught us that we have to treat the space and time in equal footing. So what are the possible terms we can write? So we have box of mu. Remember, box is the D'Alembert operator, which is del square minus 1 over this square delta t. In terms of index notation, which is a scalar. Remember, if it has to be correct in tensorial equation, both sides has to be the same amount number of free Lorentz indices. This left hand side should have one free index. First term is consistent with that. Then we can have this del dot A is nothing but del mu mu nu, and then we can also have 3 times mu nu, and this is equal to change. Now we have these 3 undetermined coefficient a1, a2, a3. We have to fix it. So we will have to impose some more conditions, and let's see what they are. So first, let's look at the mu equal to 0 component of this equation. If a1 box of a0, a2, del 0 of a, a3, j0. Now let's consider static limit. Okay. In that limit, we expect that the fields are not function of time. So any time derivative of it will be 0. So in that limit, this term containing the a2 is 0 because it's del 0 of some a. So now we can rewrite this and get the following: del square plus a3 a1 a0 by a. Okay. And j0 is of course c times rho. Okay. Not going to write it explicitly at this point. Also note that effectively the box or D'Alembertian will behave as a Laplacian in the static limit because the time derivative acting on del 0 gives you 0. Okay. That is why we just written is the Laplacian. Now this equation is of the following form: del square minus some m square function some so j. This is of this form, right? Where this m square is nothing but this minus of this a3 by a1. So this is basically an equation of a massive scalar field with some source j. And this is an inhomogeneous equation. You can solve it by a standard Green function method. And if you consider a point charge like source, so this source term j will be proportional to some delta function point source. In that case, the solution of phi, you can write it as minus m times is the exponentially damped solution. So for our case, now translating everything back in terms of a0 and this coefficient a3 a1, we can have the following solution. Let's write it down: a0 is up to some proportionality constant, we don't care, is I exponential plus minus A3 by A1 times so note that when we write the solution, we assume that whatever this is inside the square root minus A3 by A1 is a non-negative number, and in that case, it is exponentially damped. Or if it is opposite, that A3 by A1 is itself positive, so whatever inside square root is negative, then we will have a sinusoidal solution. So this is for the case that H3 by 0, and you can have sine or cosine of square root of H3 by A1 times and this is for H3 by A1. But now we know from experiment that for a point charge, the potential fall off as 1 over r. You don't get exponentially damped solution, neither you get a oscillating solution. Those kind of solution for a point charge does not exist. We know that Coulomb's law in the static limit holds very well. So imposing that fact that we don't observe this kind of exponentially damped or the sinusoidal type of solution for a point static charge, we can set the term A3 to 0. If you set A3 to 0, then you will see that the solution will be, this mass term will basically vanish. It will be all over as 1 over r, 1 over x minus x prime mod of it, right? So we impose A3 to 0 as Coulomb law holds. Okay. So this condition fixes one of the undetermined coefficient, rather it's set it to 0. So we left with the following. Have A1 box mu plus A2 del mu del dot A equal to J mu. Now what are the condition that we need to impose to fix A1, A2? First one is that we know that J mu has to be constant. So the continuity equation, that means del mu J mu 0, implies the following. A1 plus A2 is equal to box times basically del dot A into 0. This is a very little algebra that will give this equation. You can do that by yourself. Now this implies that A1 minus A2. So we finally get the following. A1 times box mu minus del mu del J. Okay. Now again look at the growth component of this equation and take the static limit equal to 0 and take the static limit. What is that? A1. So box in the limit will be del square A0. Second term will vanish. This is J0. But what is J0? J0 is rho times C. But in this limit, we expect that we should recover our Poisson equation for electrostatic. If you compare with that, so A0 with this electrostatic potential phi, so we must have minus del square phi is equal to rho. And A1 in that case will be minus C to recover the Poisson equation. That is that's always a consistency check. The appropriate limit from in the special relativity, you should get back your Newtonian physics. So now we have determined everything, and finally we have the following: del mu a box of a mu j mu nu I c. And now you can see that if you define a field strength which is of this form, then in terms of this f mu nu, you can write this equation as follows. So this is nothing but the inhomogeneous Maxwell's equation. That is the Maxwell's equation with force. So we have arrived at a Lorentz covariant version of the Poisson equation of electrostatic, which is the inhomogeneous Maxwell's equation, which is what we know, right? So the lesson that we learned here is that by imposing the Lorentz covariant as well as restriction of derivative on the fields to second order, also the non-existence of damped or oscillatory solution for a point charge, as well as the conservation of charge, and get the Maxwell's equation, which is explicitly Lorentz covariant, from a non-Lorentz covariant equation of electrostatic. The potential form of from electrostatic. And these things we will repeat for the equation for gravity. So we impose this kind of physical condition with some suitable modification. Those conditions also similar to this, but has to be appropriately modified. We'll discuss that, and we'll see what Lorentz covariant equation we will write. Before we end, we make one comment. So we note that this equation possesses a gauge symmetry. So under a gauge transformation, the form mu nu, where chi is an arbitrary scalar function, Maxwell equations remains invariant. And we consider this gauge symmetry as a fundamental symmetry of this theory. Whatever coupling with matter we can write for this Maxwell field must respect this gauge symmetry. Okay. And in the next lecture, we are going to utilize this and try to derive the Lorentz covariant form of the point charge in a background electromagnetic field, starting from its non-relativistic version. We'll end here, and thank you.